So you downloaded and installed MLOPs and downloaded your first model, just as Paul covered in the previous video, and now you want to build something. The first hint I want to give you is that under the installation directory where you copied your MLOPs to, in my case that lives in the documents, there's a subfolder called hip, and in there lives a demo file, which contains a lot of examples, also some of the stuff that I will be talking about now. So your first setup, let's start with a very simple text-to-image node tree by dropping down a geonode, diving in there, and then let's start building our MLOps tree. And in this case, I want to start with a prompt create, which is an input field for a string where I can prompt for something. Like this. Then we have to feed this into a tokenizer, which when highlighted will convert our input string into tokens, which are a bunch of integer numbers, which we can see here. And they are basically just a mapping from individual word snippets into integer numbers. We're going to feed them into a text encoder, which again will transform those numbers into a bunch of floats, 87,000. And this is a high-dimensional vector that guides our denoising process, our solver, into a direction into which it should denoise the initial noise that we feed into the stable diffusion algorithm. If you look at the geo spreadsheet, you can see there are two types here, the conditional and the unconditional embedding. And you can also see two inputs here on the text encoder, one for a positive and one for a negative prompt, which then get converted into these two attributes. So let's provide a negative prompt by just also creating a prompt create. And we definitely don't want an ugly image. We do not want a bad image. We don't want anything that's mangled or skewed. And let's tokenize this as well. And then feed it into the negative prompt here. All right, with that out of the way, we can start setting up our solve and our solver to turn this into an image. We do this by creating a scheduler first. And the scheduler is kind of the node that connects all the inputs and all the parameters that configure and go into the stable diffusion denoising process. With the first input requiring the text embeddings, and the second input requiring an initial noise stored as latents. And you can think of latents as another very clever way of storing an image, just very compact without losing too much detail. In this case, we just want to feed in a latent noise generate here, and in here we have to set up the image height and width that we are prompting for. With some models, I had the best experience with square images. However, some or most of these models should also work with non-square images. For now, I'll leave this as a default setting, and keep in mind that if you want to change the seed of your generation, it's in here. So that goes into the second slot. Later, for image to image, we've got an image input here, as well as a mask input. So after the scheduler, we will attach our solver, but before we do that, on our scheduler itself, we have a bunch of parameters here. For text to image, the two important or the three important ones are the CFG scale that drives how strongly stable diffusion adheres to the prompt. Higher values such as 10 make it adhere better to what you prompted. However, at some point you will see artifacts with lower values giving stable diffusion a bit more leeway in the creation of the image. The scheduler drives how the image has been denoised, with UniPC being a rather new implementation, which in our testing generated quite good results with a low number of inference steps. Some techniques, however, only work with a certain scheduler, usually the Euler discrete or Euler ancestral. Keep that in mind. For now, we're going to stick to UniPC. 20 inference steps is plenty, and the image guidance strength we can ignore for now, as we're not doing image to image. It goes into the solver. The solver has a second input for control net inputs. We're going to talk about this in a later video. And then we can highlight and run the solver, which will take a short while to start. And then you can see this progress bar. And now if we zoom out a bit, you can see we generated a bunch of points here. However, there's no image visible. That is because these are the latents. Remember this compressed version of our image that we just generated. And we can visualize the values stored on those latents just by dropping down a color node, wiring this in here, and then setting the color type to ramp from attribute, and we want to ramp from the latent. And if we highlight this and maybe set our background to be dark and disable the grid, we can already see some image appearing there. However, that is not really what I was going for. So let's turn these latents into an actual image using the SD image decoder, which will wire in after the solver like this, then visualize this. And you can see now we've got a bunch of points with, well, a capybara that is hiding its head. So let's change the latent noises seed a bit. And although it has a few artifacts, for now, I'm happy with this. All right, if we want to save out this image, which currently is just stored as a bunch of points in a plane, we can use the SD export image node, wire this in here, switch the view flag on, and now let's make sure that we have the lighting disabled. And also, if you've got OCIO installed, just go here, display the correction toolbar, and then set your output to raw. So we can now specify an export path and just hit export if we want to save only one image, or hit auto cook, and maybe let's create an animation or a series of images by in our SD latent noise generate, just tying the seed to our frame by typing in $FF in here, then closing this, letting the solver run, and then on our SD export image, make sure the output path is right. I'll just like doing it like that. Make sure autocook is enabled, and then we just hit play on the play bar. And as soon as a new image is generated, it will be displayed and automatically exported. So while this keeps generating capybara images, that is my whole node tree here, which you can also find in the example file. And this is our very first Stable Diffusion setup using MLOPs in Houdini. For more info on the toolset, stay tuned. Consider following Paul Ambrosiuson on Twitter or Entagma on Twitter, as in the upcoming days we will be publishing quite a few videos on the toolset that we designed. And also, if you want to participate in the development, in the trajectory of those nodes, want to share ideas, or maybe find some help or like-minded people, take note that in the GitHub here, down here, there's a link for a Discord server that you can join, where you'll find some of the beta testers for this plugin, as well as Paul and myself, and we are very open to your feedback. Thanks so much, and have fun using those tools.